Hello everyone. Today I will talk about our paper evaluating the effectiveness of decompilers. So this is a joint work with colleagues from the Chinese Academy of Science. Decompiler is widely used in binary program analysis. When using a decompiler, we expect it to generate code that retains the same semantics as the original binary, while being easier to understand compared to assembly code. However, in practice, the code generated by decompilers is often highly mechanical, and for less experienced analysts, understanding the decompiled code can be more difficult than understanding the assembly code. This is especially true for highly optimized binaries or strict binaries. Why can't decompilers generate code that satisfies our expectations? We analyze the decompiler process. Similar to compilers, a decompiler converts assembly code into intermediate representation, then applies a series of optimization passes to gradually lift it to source code. Further optimizations are performed on the source code as well. Therefore, we believe that the code generated by current decompilers is still a semi-finished product, somewhere between assembly code and a perfect decompilation. However, there is still a lack of systematic evaluation of how far this semi-finished product has progressed and how much room for improvement remains compared to perfect decompilation, particularly in the context of decompiling optimized binaries. Therefore, this paper conducts a systematic study on the current state of decompilers. We evaluate the correctness and readability of decompiled code from commonly used decompilers in practice. We aim to answer the following research questions. We evaluate the effectiveness of decompilers across 4 key areas. First, recompatibility. We analyze the challenges that prevent the recompilation of decompiled code and the potential for automatic repair. Second, semantic consistency. We introduce a random testing pipeline to detect semantic errors in control structures and data flow. Then readability. We evaluate current optimization strategies used by decompilers and identifying factors that hinder code readability. Finally, human study. We investigate the role of decompilers in reverse engineering and examine the gap between decompiled code and perfect decompilation. Existing evaluations of decompilers generally assume that for non-optimized code, decompilers can generate recompilable code. However, in practical analysis, analysts more often deal with highly optimized binaries that have had symbol information removed. So does the same apply to optimized code? We conducted an evaluation to answer this question. We ran syntax checks on the decompiled code, extracting user-defined functions and adding decompiler-specific headers to handle custom data types. By analyzing error messages and the related code, and using an automatic repair tool to fix the compilation failures, we evaluated how challenging it is to correct these errors. The results show that most decompilers encounter difficulties in generating directly recompilable code, and repair these errors remains a significant challenge. Then we propose a method for evaluating the semantic accuracy of decompiled code that does not rely on recompilation. We propose a random testing pipeline to detect the semantic errors in decompiled code. Our primary goal is to identify as many errors as possible related to the semantic reliability of decompilers. So the test cases require binary code that is as complex as possible. To achieve this, we developed a random code generator capable of producing complex source code called Dismiss. The generator ensures the complexity of the binary code by avoiding operations that are easily optimized. The semantics of functions generated by Dismiss is to return a checksum summarizing the computation performed by the program as shown in this listing. After obtaining the test cases, we check the semantic of decompiled code. We extract symbolic expressions representing the semantics from both the decompiled code and the original code's intermediate representation. By comparing these two expressions, we can verify the semantic accuracy of the code. To facilitate checking the data flow and the control flow of functions, we instrumented the code with data flow and basic blocks annotations, as shown in the list. We designed an automated method for comparing and error localization. We use three metrics to evaluate the two symbolic expressions. The first is similarity, which measures the edit distance between the two symbolic expressions to assess the semantic similarity between the decompiled code and the ground truth. The advantage of this approach is that while it may be difficult for decompiler to produce completely correct function-level results, even with some errors, the semantics it provides can still be vulnerable for analysts. Our goal is to measure the semantic difference compared to the ground truth rather than just evaluating correctness or incorrectness. Certainly, we also measure the accuracy of semantic. Through concurrent testing, we gather statistical information on how accurately the decompiler is able to recover the data flow. Finally, it is worth mentioning that to speed up the identification and analysis of decompilation errors, we record token positions in symbolic expressions during our symbolic execution. This approach allows us to pinpoint error statements in the decompiled code or intermediate representation. Through our evaluation using random testing, we found that although compiler optimizations pose challenges for decompilers, current decompilers have demonstrated good robustness across the various optimization levels. Notably, Hicks rates achieved an average semantic similarity of around 80% between the recovered code and the original binary. Upon further analysis of the identified errors, we discovered some false positives. Different decompilers translated the same low-level code segment into different high-level representations. despite maintaining consistent semantics. For example, as shown in the figure, a not instruction was translated into a very complex piece of code by Ghidra. This highlights the limitation of rule-based approaches. Then we evaluated the readability of the decompiled code. We focus on how decompilers organize and express code with identical semantics but in different structures. The evaluation results indicate that decompiled code is still largely a direct translation of machine code with limited use of common human programming partners. The resulting code tends to have a low level of abstraction, making it difficult to reflect the original design intent of program. We believe that it is difficult to overcome this limitation using heuristic-based decompilation methods. Finally, we conducted a human study by organizing a competition. Participants were asked to complete 3 tasks on a website we provided, gradually optimizing decompiled code until it reached a state of perfect decompilation. By monitoring the actual process of user fixes, we were able to assess how much assistance the decompiled code can provide, as well as identifying the information users could not directly infer from the decompiled code. The 3 tasks were as follows. First, only decompiled code is provided to fix the compilation errors. Then provide decompiled code only to pass all test cases. Finally, provide decompiled code and disassembly comparison. Try to achieve perfect decompilation. We build a platform for fixing decompiled code based on the platform provided by the authors of Decompilers. This platform allows participants to engage in tasks focused on correcting and improving the decompiled code. The results show that participants were able to successfully correct the semantics of some tasks used only in the decompiled code, indicating that decompilers can provide useful insights into program logic. However, there remained a significant difference between the repaired binary and the original binary. Achieving a higher degree of similarity between the repaired code and the original binary required iterative adjustment based on disassembly difference, which is beyond what current decompilers are capable of providing. In addition, we found that most of the users' modifications were not deserved directly, but rather required a chill and correct approach, meaning that they could not be completed through deterministic reasoning. This highlights the limitations of rule-based methods for this task. The observation reveals a new direction for optimizing decompiled code, suggesting that future improvements should focus on approaches beyond rigid rule-based systems to better support user-driven code refinement. Based on our evaluation across these 4 areas, we believe that the accuracy of static analysis proved to be the primary limiting factor affecting the quality of decompiled code. Recompilable decompiled code can aid in correcting errors in the decompiled code. And we believe that introducing compilation feedback strategies such as a speculate, verify, and correct approach could offer a more effective method for optimizing decompiled code. This approach allows for iterative improvements, enabling better alignment between decompiled code and the original binary. Our code is already available on GitHub and is continuously being updated and iterated upon. That's all. Thanks for listening.